So for lab two, we had to our main task were designing and testing, simulating multiple circuits in Xilinx IC. So our first task was to design a 8-bit adder with a with eight full adders. The full adder circuit was given in the lab manual, and it is recreated right here. So full adders are basically two half adders, and they have an that are added together with an OR gate. So we have one half adder here and another half adder with this XOR and another and additionally we have the carry in that goes to the other half adder as shown. So actually that's the result of the sum, and then we have the carry in and the inputs of A and B OR to also give the carry out. And so full adder was then converted into a schematic block, and then 8 of them are combined together to make the 8-bit full adder here as shown. And here's the sample test bench that was written, or the test bench that I wrote. So if we run it, um, we can see that it works. So we have um, input of A 85, B 170, we get 255. If we add 60 to 170, we get 230. And then 60 and 195 is 225. I think carry in is 0 here. But then we're going to do 60 and 195 added together. But we have carry in that will result in overflow, so the result will be 0. And then carry out should be higher, as shown. So the 8-bit adder was then taken, then converted into schematic blocks, and then 4 of them were combined together to make 32-bit adder, which was the next task in the lab. And so here is the test bench for the 32-bit adder. So if we run 32-bit adder test file, we can see that the additions work accordingly. So you can see the additions work. So after the 32-bit adder was completed, um, the task was to take the 32-bit adder and then add a subtractor, um, the shifter, and two other components of choice. So the um, the adder was modified so that it could also subtract at the same time. So here we have the input k, which basically selects if you want to do added addition or subtraction based on its state. So low means it will not, it'll add, but if it's high, it'll subtract. Here's the shifter. The shifter is essentially a bunch of cascading D flip-flops. This is the gate implementation, but shifter basically either shifts based on the D input if it wants to shift left or right by 1 bit. And that was the 8-bit shifter, and it was grouped into 4 to make a 32-bit shifter. And here we have, so for X, my other two functions that I implemented in my entire design were bitwise operations, so I chose XOR and NAND operations. So because they're two 32-bit values, you have to do a 64 to 1 selection. So essentially, first was I designed a 32 input XOR. So took an 8 input XOR, coupled that with 4 input XOR gates to make this, and then that was combined to essentially two 32s into one XOR out, and accordingly, for the NAND, it was pretty much the same deal. So we took I took an 8 input NAND, and to those were connected 8 4 input NAND gates, and then that was coupled together into a 2 to 1 NAND that would result into a 64 to 1 NAND. And so the overall design had the adder subtractor. The output was shifted based on the input choice, shift left or right by 1. And then the output of the adder or subtractor calculation was either NANDed or XORed. And here is the test bench for the group design. So if we run the simulation, we can see that sum works. The sum is working correctly. And then if we want to actually just show if the shift works, go to binary. As you can see, shift control is off on the first test case, but on the second it was, and it did shift. So the shift is working. And we can see also that the subcontrol shell to subtract, and we can see that it did subtract when the subcontrol signal is high. And of course, we can see that the NAND and XOR result outputs are working. So for our final portion of our lab, we had to write a 32-bit ALU in Verilog. And so that is what is here. We basically have the two inputs A and B, the ALU operand select, the result of the ALU, and the carryout output. And basically what's done is in a combinational block. We have all the functions of the ALU based on the ALU op selection, bit selection. So we have addition, subtraction, multiplication, shift left by one, shift right by one, or, and um, and NOR. So the test bench was done in accordance with the design. And if we run the simulation, we can see that it is working accordingly. So addition, subtraction, multiplication, and so forth.